Yeah, thank you very much. Thanks for coming. So I'll tell you about this paper. And there are two co-authors. There's Yassine, who's a postdoc at Caltech, originally from Morocco, and Swala, who is my PhD student at UC Berkeley, originally from Iceland. So I'm retired from UC Berkeley, but they're very nice. They still let me work with Berkeley students, and they're all in Leipzig right now. They love to come in the summer. Universe Plus is the name of the collaborative project I have with three physicists, and I'll say more about this as the talk goes on. So in the pre-session, I gave this puzzle to the people who showed up, and the puzzle was to find all 4x4 symmetric matrices with zeros on the diagonal that have rank 2. Okay, so this is described by the vanishing of the 3x3 subdeterminants, the 3x3 minors in the 6-dimensional space with coordinates A, B, C, D, F. This is going to be the variety V1, 4, 2 in the relationship in the notation later. And this is the last 4 lines is what you type into your computer to get the answer. So this is Macaulay 2 code, but you can just scan it into ChatGPT and you'll get the answer. And this is the logo. So the collaboration with the physicist is called Positive Geometry in Particle Physics and Cosmology. So positive geometry is something that certainly involves complex real and tropical geometry. This is a cartoon of a scattering process, a particle scattering, maybe at the Large Hadron Collider at CERN. And on the right side, there's a cartoon for a 3-point function in cosmology. Okay, so we'll come back to this. Let me start out with 6 vectors, P1, W1, P2, W2, P3, W4 in R-dimensional real space. And I would like them to be isotropic in the following sense. I want the inner product of Pi with itself to be 0, each vector. And then also for fixed index I, I would like the inner product of Pi and Wi to be 0. So these are my constraints. A dot here is a quadratic form, so it's given by some symmetric R by R matrix. And this condition of dotting itself with itself to 0 is usually called isotropic in linear algebra and representation theory. Okay. Now in physics, a quadratic form that's get used a lot is this quadratic form. So it's almost the usual inner product, except you have a -1 here. And this is the Lorentzian inner product. So this gets used when we speak about the 4-dimensional space-time that surrounds us with 3 space dimensions and then the -1 for the time dimension. Then here the I, 1, 2, 3. This refers to 3 massless particles, such as photons. And the momentum vectors, so the Pi, they're called momentum vectors, and the Wi are called polarization vectors. And this condition of dotting to 0, this forms the light cone. So this is the light cone, and the universal speed limit says you have to stay inside the light cone, but you could be really fast, like a photon, and be on the boundary of the light cone. Now in mathematics, physics, and many applications, we maybe don't care so much about the vectors themselves and their coordinates, but we really are interested in geometric or physical quantities, so we're interested in quantities that are invariant under the relevant symmetry group, and the symmetry group here is the special orthogonal group, so these are R by R matrices that preserve the quadratic form, the special orthogonal group. Also notice that I have only 20 slides, and we're already on slide 3, so please interrupt me with questions. And as always in the calculus class, right, if you don't have questions for me, I will have questions for you. Okay, so these inner products, we can stick them into a gram matrix, the 6 by 6 matrix. So the gram matrix of a bunch of vectors records the pairwise inner product, and in our example, I have this, my 6 vectors here as the row vectors of this 6 by R matrix. In the middle, I have a symmetric R by R matrix for the inner product, and here the transpose an R by 6 matrix. And then this is symmetric, but my hypothesis here ensures that I have 2 by 2 0 blocks along the diagonal. This was my isotropic assumption. Maybe a question we could ask is, what is the rank of this matrix? Well, the answer is the rank is at most R, right? If you have a 6 by R matrix times an R by R matrix times an R by 6 matrix, then the rank is at most R, and typically it will be R. Now, how can we study this situation? Well, in computer algebra, we would maybe ask the question, what are all the matrices of a given rank that look like this, right? So we would set up a polynomial ring in these 12 variables, x13, x14, up to x46, and the rank constraint saying that the rank is at most R means that the R plus 1 times R plus 1 minors vanish, and we compute the ideal. We look at the ideal of R plus 1 minors, and then we're interested in the variety or 0 set of these minors of this ideal. So what is this variety? So how should you study this? Well, you should use computer algebra, right? So if you're using Mathematica, you try Mathematica or Sage. In my community, Macaulay 2 is pretty popular. OSCAR is increasingly popular. OSCAR is the German computer algebra system. So that stands for Open Source Computer Algebra Research. It's a DFG-funded national project, mostly centered at Kaiserslautern, Saarbrücken, and Aachen, but has some other nodes, and it's getting better and better. There are more and more users, and so this is sort of the German answer to Sage. But in any case, whatever you do to do mathematics on the computer, you should try this. You can try these kind of questions. And in the pre-session prior to the coffee, some of us tried already. Right? But let me do this for you, step by step. So the underlying workhorse in computer algebra sometimes is Gröbner bases. And let's explore the 6 varieties given by rank constraints. Yes?
What are the 12 unknowns? Because I could find only 8.
Oh, here, x13, x14, x3. So there's 4, 4, and another 4. Right? So this matrix, so a 6 by 6 matrix, if it's a general matrix, has 36 entries. If it's a symmetric matrix, it has 21 distinct entries. But here, these 3, 3, 3 entries along the diagonal are 0, so there are 12 left. Right? So my constraints leave 12, so I'm working in a polynomial ring in 12 variables. Okay? I'm writing down a system of polynomials, and now we're going to investigate this together for rank 0, 1, 2, 3, and we see what we get. Okay? That's the plan for the next 5 minutes. Okay, well, let's start with rank 0, right? So a matrix has rank 0, well, that means it's a 0 matrix, right? So the 1 by 1 minor, so therefore ideal contains all the 12 variables, so the variety, the solution set is just the origin, just the 0 matrix, and the dimension of the solution set is 0 dimensional, it's just one single point. Now, what about rank 1? Well, rank 1, now the ideal is given by the 2 by 2 minor, so we make the 2 by 2 minors vanish. So it turns out that the only solution is still just the origin, but now it's a bit more interesting. It's a point with multiplicity 13. It's like a fat point. So just like if you have multiplicities of roots of polynomials in one variable, here we still have a 0-dimensional solution set, but the multiplicity will be 13. So what I'm going to do on this slide, I'm going to highlight nouns in red and adjectives in blue. Okay? So for example, Gröbner base is the workhorse and multiplicity is a technical term. It just says it's sort of a chunky fat point. r equals 2. Now we look at the 3 by 3 minor. So it turns out that the variety has 3 irreducible components. So a variety is irreducible if it cannot be written as a union of 2 other proper varieties. But this one is reducible. It has 3 irreducible components. They have dimension of 5. But it also has so-called embedded primes. So this I should maybe explain. So if you have a system of equations, so somebody, asks you, somebody asks you to solve these equations, right? So when the plane, and we like the solution set where x squared is 0 and xy is 0. Right? Well, so naively, this is the same as just setting x to 0. This is just the y-axis. But actually, this ideal decomposes as x squared y intersected x. So really, there is a line, but there is a so-called embedded fat point. So this additional component has an embedded point, and this is what happens here. So there are 3 5-dimensional components, but in addition, there's sort of an embedded component, and there are 4 of them. Now for r equals 3, the variety is toric. So toric varieties are super nice. They are defined by the nicest equations. In particular, toric varieties are irreducible. So this is a 6-dimensional toric variety. The ideal is primary. That's a blue adjective. But it's not radical. That is a blue adjective. Okay? So commutative algebra is the study of blue adjectives. Let's look at rank 4. So now we make the 5 by 5 minors vanish. So now the ideal is radical, but not prime. Now there are 4 irreducible components. One that we like in particular, so this comes from the cosmology application we'll talk about later, and there are 3 others. But altogether, the variety has dimension 9 or codimension 4. I'm sorry, codimension 3. Well, we're in a 12-dimensional space, and the codimension is 3, the dimension is 9. Now, last but not least, like rank 5, right? Well, rank 5, there's only one equation. This is the 6 by 6 determinant of our matrix. The 6 by 6 determinant is an irreducible polynomial in 12 variables, so it generates a principal prime ideal. Okay? So there are a couple things about this slide. So one thing, it's useful to have an algebra language to speak about this kind of stuff. Right? I mean, it's very, very useful if you want to communicate the structure of these solution sets, to have a little bit of blue and red language. The other thing that you see, it looks very erratic, right? So all kinds of things can happen, right? So even for this small 6 by 6 example, different kind of behavior seems to occur, and we just explored this in our experiment here. Let me give you the general definition. So I'm going to fix 3 integers, k, n, and r. So we're going to be interested in symmetric kn by kn matrices that have 0 k by k blocks along the main diagonal. So this is the formal description. So now I'm forming the polynomial ring for convenience over the complex numbers, but that doesn't matter. So I have these variables xi, j. So I'm counting the variables, right? So I have kn rows, so the number of entries in a symmetric matrix is kn plus 1 choose 2. But then I have n 0 blocks, so I have to subtract n times this other binomial coefficient. So the number of variables is m, and I'm going to write v, k, n, r for the variety in this m-dimensional space consisting of all matrices of rank at most r. That's the object I would like to study. Right? So 3 parameters. N is the number of blocks. Later on, that will be the number of particles or fields. K is the size of the 0 blocks, and r is the desired rank. So for example, we could ask, what is V233? Okay, let's think about this. So So 2 times 3 says we're supposed to look at a 6 by 6 matrix. The desired rank is 3, and I have 2 by 2 0 blocks on the main diagonal, right? So this is the R equals 3 case here. This is this very nice toric variety. It's a degeneration of the 2,6 Grassmannian. Very nice degeneration. Okay, so let me state a first theorem. So the way this talk will go is that if you have trained in algebra a little bit, everything will be very understandable and easy. If you're not trained so much in algebra, just bear with me, right? I mean, there's all these adjectives and nouns, you know. But then there will be a second part of the talk. We're going to get into the physics, which means for me it gets very, very hard and maybe less comprehensible. We'll see how it goes. Anyway, here's a clean algebra statement. So if we're in the high rank regime, so if R is at least 2k plus 1, k is the block size, then the variety is irreducible, meaning I cannot break it into pieces. And the dimension of this variety is this number, this explicit number that depends on n, k, and r. That's a positive integer. Here's the dimension of the orthogonal group. And so this says the variety is very nice and irreducible. Algebraically speaking, the minors generate the prime ideal. So they are prime ideal. And there's one more blue adjective. It's Cohn-Macaulay. That means there are no embedded components, and also the dimension is sort of what you would expect from parameter counting. Right? Very good. So this says things are nice. Now, of course, R has to be at least 2k plus 1. So in my example, 2k plus 1 would have been 5. Right? So in this example, this only, you know, pertains here to the R equals 5 case. It's nice and irreducible, but we have this erratic behavior further up in the table. Right? Okay, so this theorem says in the high rank regime, things are nice, and the dimension is as expected. Actually, even the case of 1 by 1 blocks being 0 is interesting, so let's have a slide on that one. So if k is 1, we're looking at symmetric n by n matrices that just have zeros on the diagonal. Now, in this case, the high rank regime says R is at least 3. So 2k plus 1 is 3. For R equals to 3, it's a very special variety. It's a so-called squared Grassmannian. In probability theory, this occurs for determinantal point processes, so it has a very nice statistical meaning. Now, for R equals 0 and 1, it's just the origin, but an interesting case is R equals 2. And this is the puzzle. Right? So for R equals 2, we have, for example, n equals 4. We have the variety V, n, 4, 2. And that's the variety of these matrices of rank 2. Some of you thought about this. The postdoc figured it out. You were at the blackboard, right? And this is what Macaulay 2 gives you back. Right? So you type this into Macaulay 2, or you take a picture for ChatGPT, then you get this answer, right? There are 7 irreducible components. All of them have codimension 3, that is to say also dimension 3. So for example, ideal ABD means you can make those 0 and the other ones non-zero. So this says you just retain the last row and the last column and everything else is 0. Then by symmetry, you have these others. And then finally, for example, here you can make A and F vanish, but then this 2 by 2 block up here has to be 0. Right? So the 3 solutions say that 2 of the variables are 0, and then the complementary 2 by 2 matrix has rank 1. There are 7 components. Now in general, this variety V1n2 has 2 to the n minus 1 irreducible components. That's the number 7. Each has codimension n minus 1 choose 2. That's the number 3. And the total degree, if you add up the degree of these varieties, is 2n minus 3 choose n minus 2. And that's the number 10 in our example, right? So the degree, these linear pieces have degree 1, and these quadratic pieces have degree 2, And then, 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 2 makes 10. Okay? This is a proposition that solves this puzzle for n by n matrices. Now, why do we get these sort of interesting? These results that I'm presenting here, they were kind of new. They're new in commutative algebra. And I think what I encountered in applications, usually the symmetric matrices that we see have a lot of action on the diagonal. In statistics, they're usually, covariance matrices of Gaussians. They're positive definite, right? In optimization, semi-definite optimization, more often than not, we see positive definite matrices. And a positive definite matrix has a lot of stuff happen along the main diagonal. But here in this physics application, where we have a Lorentzian inner product, it's the opposite. We have vanishing along the diagonal. And I think for me, this was quite a new experience. And also, I think this hasn't been, these particular results were new. Let me state another slide with two theorems. So this is a slightly more general version of the theorem that covers all possible cases. So this theorem gives a formula for the dimension. So again, we have the parameters r for the rank, n for the number of blocks, and k for the block size. I'm going to write L for r over 2 rounded down. So then in the high rank regime here, if r is at least 2k minus 1, that's the previous number. But if r is at most 2k plus 2, then you get this number that also has the L in it. But it depends on n, k, and r. In the second case, again, the ideal is nice. And there are many blue ways of saying nice in commutative algebra. And here the niceness is called Macaulay. A fun exercise is to check that there's an overlap, right? You can see there are 4 ranks where they overlap. It's a fun exercise to check that these two numbers are the same if r is in this rank. Right? So I claim that if r is in this range, this expression is actually equal to this expression. Okay, so that's a formula for the theorem. Now the second theorem here, the second main result about this topic is a characterization when the variety is irreducible. So our variety Vk nr is irreducible, meaning you cannot break it into pieces. If and only if r is odd, either r is odd or r is in the high rank regime, which means that r is bigger than 2k. So if r is even and between 4 and 2k, then the number of irreducible components, just like in the 1 by 1 block case, is 2 to the n minus 1. But if r is 2, as in the puzzle, then it's 2 to the n minus 1 minus 1. Okay? So those are the algebra statements we have about these matrices, symmetric matrices with rank constraints having zeros along the block. Now, of course, it's nice to prove theorems. It's sometimes even nicer to perform hard calculations, right? So let me talk a little bit about data, right? So we found explicit parameterizations of all the irreducible components, and we computed the ideals in many cases. So this is just to kind of give you a sense what the data look like. So here is k and n for the columns. So for example, 2, 5 means we're looking at 10 by 10 matrices with 0, 2 by 2 blocks. And then the rows are for the different rank. Okay. Now dimension is the degrees of freedom of this variety. So degree is how curvy are you. Right? So it's the degree of the variety. And then the number of ideal generators is the third number. So for example, if we look at here this case, 2, 5 of rank 4, so the variety is dimension 19. The degree is 306,735. And the number of generators, which all have degree 5, the 5 by 5 linearly independent 5 by 5 determinants are 19,404. Right? Now, these kind of computations, especially as far as the degree is concerned, you cannot do with symbolic computation. So until maybe about 10, 15 years ago, the paradigm of computing in algebraic geometry was symbolic computation. That is to say, Gröbner bases and things like that. But that only goes so far, right? If you ever tried Gröbner bases on your problem, well, at some point, they just don't terminate, right? So there's a limit to how far you can go with exact symbolic computation. But nowadays, as about 10 years ago, there's a very active area of numerical algebraic geometry, and with numerical methods, you can go further. Now, algebraists used to be scared of numerical methods, right? So things like condition numbers, and rounding errors, are scary to algebraists. However, nowadays, these methods are accurate with proof, okay? So with interval arithmetic type proofs. So nowadays, we also, in addition to symbolic computing techniques, we can also use numerical methods. So these smaller numbers here, you can find this with symbolic techniques, but once the degrees get into the 100,000s, you can only do this with numerical methods. Okay, well, the talk is almost half over. Are there any questions? Yes?
So I have a question regarding the first line. So you said that you have explicit parametrizations, and the first question is, do you have this for general, K, N, and R?
Yes.
And then is this a theorem, or is this something what you also compute?
We actually have a theorem. So in general, what we're saying is we know what these components are, and we can describe each component as the image of a map, as a parametric representation. So here, these are very simple, right? One by one, rank 1 matrices have a very simple. A rank 1 matrix looks like this, right? A rank 1 matrix is a column vector times a row vector. So I'm acting out the parametrization of a rank 1 matrix. You can also act out the parametrization of a rank 1 tensor, right? Okay? But we have parametrization, so we break it into components, and there's a theorem. It's a little complicated, so it involves, symplectic Grassmannians and a bit more, slightly more advanced representation theory, but it's very explicit. Other questions? Okay, so this was supposed to be the understandable part. Now we're going to get to physics. Okay? Now, in this collaboration, as I said, this is called positive geometry in particle physics and cosmology, and we had our kickoff workshop last August, and this was right after the posting of this paper. So one of the team members is Daniel Baumann. He's the cosmologist. So he's a very prominent young theoretical cosmologist based in Amsterdam. And they just had put out this paper they were very excited about, a new twist on spinning ADS correlators. So ADS stands for anti-de Sitter. This is something that differential geometers know. And there were some structures in there that got me very, very interested, so we started talking, and this was really this conversation that led us to Gram matrices for isotropic vectors. So this is conformal field theory, and it's something that I know very little about, but maybe there's somebody in the room who knows more, but let me try, right? So in conformal field theory, we are interested in a field theory, let's say on a d-dimensional space that's invariant under the conformal group. So the group of conformal transformations is a big group, okay? Now, to deal with this big group, physicists have a way of embedding this into a slightly larger space where the symmetry gets realized by a smaller group. Now what we're going to do is we're going to look at a space of dimension 2 more. So R is going to be D2, D plus 2. And what we're going to do is we're going to take this flat d-dimensional space and we're identifying it with the projectivized light cone in this space, big space. So the light cone in this r-dimensional space has dimension d plus 1, but if we work modulo scaling, that is to say in the sense of projective geometry, it's also d-dimensional, so we can identify birationally this d-dimensional space with the points on the light cone up to scaling. Doing so allows us to think about conformal symmetries in the small space simply as the action of the Lorentz group, the special orthogonal group, on the bigger space. So now we really can use SO. Now, particles in particle physics, in cosmology, these things are called fields, right? So I don't know anything about the standard model, but the mantra is that a particle is an irreducible representation of SUN. But there's much, much more to this. It's called the standard model of particle physics. But what particles are in particle physics becomes fields in cosmology. Now, both fields and particles have many, many, many representations. So in particular, each of them has a momentum vector pi and a polarization vector wi. And so the I ranges from 1 up to n. N is the different fields that we have. Now this, just as the beginning of the talk, leads us to a 2n by 2n gram matrix of rank r, right? These vectors are in r-dimensional space. But from now on, the block size is k equals 2, because we only have these two flavors of vectors. So from now on, for the rest of the talk, k is equal to 2. We're going to have 2 by 2, 0 blocks. Now then I talked to my friends. I said, oh yeah, this is well known, you know, and this is a reference. This is one reference, but many of the ideas actually go back to Dirac. But there's this nice reference, spinning conformal correlators. It's always interesting to enter a new community and learn about the culture, right? So a lot of these people publish in the Journal of High Energy Physics. Now in mathematics, when we write a paper, it takes a long time, and we submit it, and the refereeing process takes forever. Right? Now in physics, I just had my first paper in this journal. Well, we wrote the paper, we submitted it, you know, and 3 weeks later, we got a referee report, and then another 4 weeks later, it was published. Right? So it's a very, very different community, very different cultural experience. Right? Okay. Now, what we're going to do is we're going to make things more complicated and more physically relevant in 2 steps. So we're going to have 4 levels of coordinate systems. So at the very beginning of the talk, we had our momentum vectors and they had coordinates. And I said these coordinates are not so interesting. Really what we're interested in is the SON invariant properties. Those are the entries in the gram matrix. But now there's going to be 2 more levels of symmetry that we're going to go up that make it more complicated. So the first level of symmetry, so the way polarization momentum vectors work is that really the quantities we're interested in conformal field theory are also invariant under the shift, where Wi gets replaced by Wi plus some constant alpha I plus pi. Now in the physics literature, there are some quote-unquote well-known conformally invariant structures. So I've written them here in the entries of the gram matrix, or here in terms of inner products. So for example, Pij is this particular, is Pi dot Pj. Well, that's obviously invariant, right, because this doesn't do anything to Pi, right? Then there are certain 2 by 2 minors of the gram matrix that are left invariant. I'm going to call them Hij. And then there are these ratios. There are some other 2 by 2 minors divided by the upper left entry that are also left invariant. Now this kind of group action, additive group action, if you've never seen this, looks simple, but it's actually very complicated, right? So we know, thanks to Hilbert from 1890, that if you have a reductive group, like as SON or GLN, the ring of invariants is finitely generated. There's a finite list of invariants, thanks to Hilbert, that generate the ring of all invariants. But if you have an additive group action like this, it's not reductive. So in general, we cannot hope for a finite list of ring generators for the invariants. However, we checked that these generate the field of invariants, and that's good enough for the following discussion. But for the physicists, these things are well known. Okay, so let's look at this. So let's use them to maybe express our varieties, right? So we're interested in V2NR. So these are our gram matrices with 2 by 2 block 0. And as I said, from now on, k is 2. Well, for example, if we take the n equals 3 case that we looked at on my example, r equals 4, It turns out that the ideal is very, very, very simple. The main component has just this representation. Now this looks inhomogeneous, but it actually, there's a grading, there's actually a homogeneous ideal, and there are two terms. So this very, very simple expression for this one, where I said there's a main component and this is the main component. Okay? Here it's given by a rather long list of 5 by 5 minors, right? But here in this formulation, suddenly it becomes very simple. So I was emboldened. I said, well, that's great. Let's move on and see whether, maybe we can use these conformally invariant coordinates to go further. And here's another example, right? So it turns out the Gram matrix, the determinant itself, has this representation. But first, a bit more joy of prime ideals. So now we're one level up, right, in terms of coordinates. So now we're making a new polynomial ring in the p, h, and v variables. So I'm introducing new variables, pij and hij and vijk. So the total number of these things is this number, and I'm going to write INR for the prime ideal in this new polynomial ring. And I'm now interested in the algebraic relations among these quantities, here in terms of p's and w's, or up there in terms of low-rank Gram matrices. Okay, so this worked out quite well. So for example, I35 in this notation is the principal ideal generated by this red polynomial, and this red polynomial is equal to the determinant of this matrix. Okay, well then we went further. It turned out it got a lot more complicated. Right? But before we get there, the first question you should always ask, the door opens, a variety walks into the door. First question is, what is your dimension? How many degrees of freedom do you have? And well, this we could show, right? This variety now in this new space has dimension 2r minus 4n, and again we have to subtract the dimension of the orthogonal group. So for example, if r is 5, we'll see that this is the case of interest in cosmology. This is 6n minus 10, and for r equals 4, it's 4n minus 6. Now why is r equals 5 interesting in cosmology? Okay? Well, if r is 5, then d is 3. Remember, we have the small space on which the conformal group acts, but the embedding space adds 2, formalism, right? So if r is 5, then d is equal to 3. But that's a little weird, right? Because our usual space-time is 4-dimensional. Why is it 3-dimensional? And the reason is, in their study, they fix time. They fix time. They just work with space. And there's a particular point in time that we're fixing. It's called the hot Big Bang. Okay? So we're fixing time at the time of the hot Big Bang. We would like to measure stuff in the sky, background radiation, whatever, and we're interested in what happened right before the hot Big Bang. Right? That's the question. So therefore, r equals 5 is the case they're really interested in, but for our mathematical analysis, it's easier sometimes to look at r equals 4. So for example, right, 4 fields in cosmology. So now r is 5 and n is 4. So in my notation, this would be the ideal I45, right? By the corollary, it's a 14-dimensional variety in a 24-dimensional ambient space. But we don't know the ideal. We know that this ideal contains 3 by 3 minors of this matrix. It contains a whole bunch of other things and many, many, many more generators. We have a long list, but we cannot actually prove right now that we have the complete list of ideal generators. So as soon as we go back, if these parameters increase a little bit, these things become quite complicated. And then we said, okay, maybe the case r equals 5, which is what really the cosmologists want, is complicated. Let's maybe try a little bit at r equals 4. So it turned out that there we could go further, and we could go further again thanks to a trick I learned from the particle physicists. And the trick I learned is called the spinor helicity formalism. Okay, what is the spinor helicity formalism? Well, it's a way of parametrizing this irreducible variety in a very, very, very clever way. what we're going to do is we're going to form a 2 by 3n matrix, a very, very skinny 2 by many matrix of parameters. The 3n columns. Okay? Now, these columns, the first n columns are called 1, 2, up to n. The next n columns are called 1 bar, 2 bar, up to n bar. Okay? So they're called. And the last ones are called, again, 1 up to n. Okay? Now, this sharp bracket here refers to the first 2 n columns. So, for example, S bar, so S is from the first n, S bar is from the next n. And this is the 2 by 2 minors of this matrix. So I'm taking 2 by 2 subdeterminants of this matrix. This angle bracket refers to the last n columns of this matrix. So I have n columns, another n columns, and another n columns, and it turns out that's another parametrization of the same variety. Okay? And that comes from the spinor helicity formalism. Well, that's a good thing, because now using this parametrization, we can go further both in computation and in theory. So first in computation, so for I5-4, so this is 5 fields at the time of the hot Big Bang in flatland. Okay, this is at the Big Bang for flatlanders. Now the ideal, we know what it is. So it's minimally generated by 180 quadrics, 20 cubics, blah, blah, blah. And there are 50 variables, so these are the well-known, quote-unquote, conformally invariant structures P, H, and V. And the dimension is 14, and the degree is 10,145. So it's this new parametrization takes us further if R is equal to 4. But there's something else that's very, very, very nice about parametrizations by 2 by 2 minors. If you have the 2 by 2 minors of a 2 by n matrix, you have the Plücker coordinates of the Grassmannian. And they have a very, very nice properties. But before we go back, let me take you to the 4th level. So these conformally invariant structures, they're nice. They have the right invariance properties, but they're not the observables yet. Really what you want is observables. And at the 4th levels, we have the observables. And what they're interested in are 2-point functions, 3-point functions, and 4-point functions. That's the kind of stuff you measure in the sky. Right? You're interested in distributions of galaxies. And a very, very, very simple, the simplest example, in the simplest theory of a 2-point function looks like this. Hij divided by Pij cubed is this expression. It's some expression in the Gram matrix. And you do this for any 2 fields. Now, of course, being algebraic geometers, now I have these n fields. I can do this 2-point function for any 2 of them, right? So I'm going to look at the rational map from my space, the variety 2nr, into the space where these are now the coordinates. So I'm mapping this into a projective space of dimension n choose 2 minus 1. And this image I'm calling the conformal 2-point variety. Okay? So that was my idea. Okay? This doesn't come from the cosmologist. This is my suggestion. Okay? So we have these n things, whatever they are. For any 2 of them, we can make a measurement. And the question I'm asking is, what are the universal algebraic relations that hold among these measurements? Right? That's some ideal. And this is the measurement variety, a variety of all possible conceivable measurements. Okay? Now, it's a nice definition. Computing is very, very, very difficult. So this is, and the reason it's so difficult is we have these layers of parametrizations. We have the 1st level plugged into the 2nd level, plugged into the 3rd level, plugged into the 4th level. Right? And that's a feature of working with people in this branch of physics. Finding the right coordinate system is often the solution. Right? So they are really working a lot. From one coordinate system, you go to twistor coordinates, you go to this coordinates, spinor coordinates. But for mathematicians working in computer algebra, following along and carrying out all of these coordinate changes increases the complexity a lot. We do have we have a conjecture about the dimension. So we believe that the conformal 2-point variety has dimension 5n minus 11. Unless it fills the space. but we can only prove this up to, I think, n equals 30 or something. We can't do this in general. However, if we go down to r equals 4, then spinor helicity helps us one more time. So it's one more theorem. This is the last theorem in this talk on slide 17 of 20. And I have 10 more minutes, 8 more minutes. Okay. So let's talk a little bit about the conformal two-point variety C2N4. So from the spinor helicity formulation, now the two-point function has this parameterization as a Laurent monomial in the brackets. Right? Remember, these are the S's and S bars. These are the names of columns in a 2 by 3n matrix, and then I have these funny brackets, right? I mean, it took a little while for me to get used to, right? So this left thing is called bra, and the right thing is called cat, and you put them together, you get bracket, okay? Well, makes sense, but it took me a little while to get used to, okay? Anyway, we have a parameterization by the 2 by 2 minors of a matrix. This means we're looking at the Grassmannian, but the G2n Grassmann is very, very, very well understood from the point of view of tropical geometry, thanks to the biologists. Our biologists, Andreas Stress, many other people worked on this, and so the tropical Grassmannian is the space of phylogenetic trees. So this monomial map tropicalizes to a linear map. So based on prior combinatorial knowledge about Grassmannians and its connections to phylogenetics, thanks to people like Andreas Stress von Bielefeld, we can now actually prove something. So the dimension of this two-point variety is 3n minus 7, and we can also sort of really analyze quite carefully the smallest interesting case. So if n is 5, then this is 15 minus 7 makes 8. In a 9-dimensional projective space, I have 5 fields. I can measure any pair at 10 measurements. When a 9-dimensional projective space, it's dimension 8. So it's a hypersurface. It's cut out by a single polynomial, and this polynomial has 200 degree 270. Right? So the combinatorial analysis that comes from these phylogenetic trees also lets us do these kind of computations. Very good. So I'm going to wrap up now on the last 3 slides. So first of all, a conclusion slide. So this project, in the end, most of the theoretical results are results in commutative algebra. Commutative algebra is a field that studies blue adjectives and red nouns. What did we study? We studied symmetric matrices with diagonal 0 blocks, and I think the postdocs here thought this was somewhat fun to do, maybe. We do understand now these rank strata in terms of commutative algebra and algebraic geometry. We then went back to the original cosmology motivation, and we introduced a new class of algebraic varieties called the conformal two-point varieties. Now, they are really more interested in 3-point functions and 4-point functions. The same concept makes sense, but then it gets even harder to compute. This was just laying the foundations. So we stuck to 2-point functions, but in our mind, they govern the relations. And again, the context here is positive geometry in particle physics and cosmology. Now, everything I said, all the algebraic results I presented work over any field. Right? So I mentioned the complex numbers, but you could also take characteristic P or the p-adics or anything. So it's really a pure algebraic result. But often, as an applied algebraic geometer, I get asked, now what about real numbers with inequalities? So typically we have an applied problem. In the applied problem, we want real solutions, and these real solutions are positive, or they're in the box, or something like this. So can you say anything? Right? So I'd like to advertise one more recent paper that actually deals with real numbers and inequalities. So there's a new paper called Kinematic Stratification. So Veronica, that's her. So she's a PhD student in Leipzig. And this is with Hadley Frost, who's a postdoc at Princeton. So one of the nodes, so the nodes for this project are in Munich, Amsterdam, Princeton, and Leipzig. And we studied something called kinematic stratifications. Here we had fun, building the light cone, right? There's the future, there's the past. You have to stay inside. That's also called causality. And the scattering process, some particles come in and from the past, and then something happens in the future. So this is about inequalities. There are many nice things about this paper. A lot of people in combinatorics these days are interested in Lorentzian polynomials, so especially after Juni Fields medal 2 years ago. And this paper is really, I think, the first that relates Lorentzian polynomials in the sense of combinatorics to Lorentzian inner product in the sense of physics. It's very gratifying. We were able to reduce and improve some calculations in physics that actually go back all the way to the 50s. That's the end of it. So if you liked my homework, this is for you guys, right? Maybe go back and look at 6x6 matrices, right? So let's look at 6x6 matrices like this with 12 unknown entries. And the question is, how can this have rank 2? What is implied by the 3x3 minors? Of course, you are encouraged maybe to learn a little bit of algebra language, right? So in algebra language, these are the associated primes. And if you like to compute some more, I'll be happy to discuss with you. Thanks for your attention.